All right, folks, welcome to 6.7, lecture on systems of inequalities and linear programming. You've made it. This is our last lecture in college algebra, so this is the final material that we're going to cover for this class. Today we're going to look at how to graph linear inequalities. We're going to graph systems of linear inequalities, and then we're going to solve linear programming problems. A linear inequality in two variables is an inequality that can be written in the form ax plus by is less than c, where a, b, and c are real numbers and a and b are not, both 0. So notice what changes this from an equation to an inequality is the symbol. We no longer have an equal sign. We have something that shows that they're not equal, that one's greater than, less than, greater than or equal to, or less than or equal to. Okay, so inequalities can use any of those four symbols: greater than, less than, greater than or equal to, or less than or equal to. The solution set of an inequality is the set of all ordered pairs that make it true, and the graph of an inequality represents its solution set. So let's look at an example to help make this more clear. Graph y is greater than x minus 4. What we're going to do when we're trying to graph these is first we're going to change them to an equation. So instead of y is greater than x minus 4, we're going to make it y equals x minus 4, which is now just a line on the graph. Okay? When we pick some points for x and y and graph, or pick a point, or pick a value for y, or I guess pick a value for x and solve for y, pick several values and then draw the line. We use a dashed line because the inequality symbol is greater than, okay, which means it does not include the equal, which is the line. So if it's greater than or less than, we use a dashed line, okay? We use solid lines if it is less than or equal to or greater than or equal to. So when the inequality also has a line under it, we use a solid line. Otherwise, we use a dashed line. After we've drawn the line, we have to determine which side of the line is shaded, because this is an inequality, so it's not just a line anymore, it's a whole area of the graph that we're going to shade. We're going to determine which half plane satisfies the inequality. It's one side of the line or the other, by picking a test point that's not on the line graph, and that's really key. Use the origin whenever possible, and the origin is not part of this equation, right? It's not part of the solution, so it's not on the line. If we look at the origin, substituting in 0 for x and 0 for y, we get 0 is greater than 0 minus 4, 0 is greater than negative 4, and this is indeed true. If a test point is true, we want to shade the side of the line which includes the point. So here's our dashed line representing y equals x minus 4. We can see that the origin, where my pointer is right now, was not on the line. When we plugged those values into the original inequality, it was a true statement. So we're going to shade the side that includes the point, which you can see here is everything above the line. Everything above the line. Okay? Now, if this point was false, if a test point is false, you shade the opposite side. So I'm going to give you an example with this same graph. So a possible test point that is not on the line, it's on the other side, is 5, 0. So we're going to do the same thing. And so it doesn't matter what point. You can pick any point that's not on the line as your test point. I just recommend picking the origin because then x and y are 0 and it makes the calculations really simple to do. So typically if I can't use the origin, I'll try to use something that's on the x or y axis. So at least one of the variables goes to 0. All right. So I'm using the point 5, 0. So let me plug that in. 5, 0, y is 0, x is 5. 0 is what? How is it related to 5 minus 4? 0 is greater than 1? No, this is false. So if this was my test point, remember, if I get a false answer, I shade everything on the opposite side of the line from the test point if it is false. You do not need to do 2 test points. I just wanted to show you 2 test points, one where the answer was true and you shade that side, the origin, and one where the solution was false and you shade the opposite side, just so you get a sense of how that works. Quick review. To graph a linear inequality in 2 variables, replace the inequality symbol with an equal sign and graph this related equation. If the inequality symbol is less than or greater than, draw the line dashed. If the inequality symbol is less than or equal to or greater than or equal to, draw the line as solid. The graph consists of a half plane on one side of the line, and if the line is solid, the line as well. To determine which half plane to shade, test a point not on the line in the original inequality. If that point is a solution, shade the half plane containing that point. If not, shade the opposite half plane. All right, so let's look at another problem. We want to graph the related equation using a solid line, 4x plus 2y equals 8. Again, the origin is not on that line. We want to determine if the origin is part of that. The origin is indeed a part of the solution, because when I plug it into the original inequality, I get 0 is less than or equal to 8, which is a true statement. So I'm going to shade the region that also includes the origin here. Okay. Notice we used a solid line this time because we have less than or equal to. We found the test points 0, 0 is true, so we shade everything on that side of the line that includes the origin. These often confuse people, although these are some of the easiest ones to do when you only have one variable. X is greater than 2 on a plane. Okay. Now, remember, we do the same thing, graph the related equation, x equals 2. This is not a point at 2, 0 on the graph. This is a line that goes through x equals 2. This is a vertical line up and down all the way through the x-axis at x equals 2. Again, this doesn't include the origin. When we put the origin in, we get x is greater than 2 or 0 is greater than 2, which is false. So in this case, we would not graph the side with the origin. And so we can see here. Again, we have greater than, so the line is dashed. Notice x equals 2 is this long line, not a simple point at the origin. And that's what throws people off. They think this is just a point, but it's a vertical line. And then again, we tested the origin. We got a false in our original inequality. 0 is not greater than 2. And so we shade everything on the other side of the line. This is very similar. Here we have y is less than or equal to 2 on a plane. And now we have a horizontal line. We're going to draw y equals 2. Again, it doesn't go through the origin. But however, when we plug the origin in, we get a true. So this time we're going to include the origin. Y equals 2 is a horizontal line. It is not a point on the y-axis. It is this entire line, which we use a solid line because indeed it is less than or equal to. We tested the origin. It was true. So we shade the side of the line that includes that test point. All right. Now let's look at systems of linear equations. This can get a little bit more difficult. But this is what I call wash, rinse, and repeat. We're going to graph each of these. We've just done several of these inequalities. Graph the line. Here we're going to do solid line. Here we're going to do dashed. And then what side of the graph that we're going to go on. And here what we're going to do is find the intersection of the shaded areas. So first we graph x plus y equals 3 using a solid line. Choose a test point and shade the correct plane. Next, we're going to graph x minus y equals 1 using a dashed line. Choose a test point and shade the plane. So here we have x plus y is greater than or equal to 3, equals 3 is this solid line, and it does not include the origin. This dashed line is x minus y equals 1. Use the test point of the origin. It does not include it, so it's below. So our area that is the solution set of the system is this little triangle. Well, it's actually quite a big. It's going to keep getting bigger and bigger as we go further to the right. But it's this triangle that you see here that is the intersection of both shaded areas. So again, when you're doing systems, you just do what I call wash, rinse, repeat. Graph the first one, graph the second one, and then look where they are intersecting. Okay. So this would be, if we're looking for the solution, it would be a solid line going down from what looks like 2, 1, a dashed line going upward diagonally at 2, 1, and then everything between those two lines, between the dash and the solid. Graph the following systems of inequalities and find the coordinates of any vertices formed. Okay. We graph the related equations using solid lines because they're all less than or equal to or greater than or equal to, and we shade the region common to all three sets. To find the vertices, what we need to do is to solve three groups of systems equations: y plus 2 equals 0, negative x plus y equals 2, and find a common point between equation 1 and 2. And then we need to find a common point, a solution between equation 1 and 3, changing these to equations again. Y plus 2 equals 0, x plus y equals 0. And then finally, we need to find the vertice between these two, which will be the common point. Okay. To find the vertices, we solve three systems of equations, the systems of equations from inequalities 1 and 2. So again here, we can see that the first equation will solve to y equals negative 2. We can plug that into the second equation and we get negative 4. When we look at 1 and 3, again we get y equals negative 2. We plug that in and we get x equals 2 to the second equation. These are pretty straightforward. And then from 2 and 3, these last two equations, here we have to do a little bit more, but notice if we add the equations together, the x's will disappear because they're opposite signs. So we get 2y equals 2 or y equals 1, and then we can plug it back in. Our graph will look like this. We really should be graphing each one of those lines and then figuring out is it above or below, but using test points. But we can see here that the solution to all three of these is indeed this triangular piece that's shaded in here. And this question specifically asks you to find all three vertices. And there's a reason that we do that, in that when we do linear programming and we're trying to find a maximum or minimum, one of the weird phenomenons is that with linear programming, those maxes and minimums of inequality systems always occur at a vertex, at a corner. So we want to find those values so that we can figure out what is the maximum or possible minimum value of a function. In many applications, we want to find a maximum or minimum value. Linear programming can tell us how to do this. Constraints are expressed as inequalities. A constraint is a very normal thing in all areas of life and work. For example, I mean, even in your own life, you have a constraint of budget. You make so much money a month, and that's all you have to spend, unless, of course, you have a credit card, which is a whole nother discussion. Okay, so constraints are like, let's say you make $1,000 a month, so your monthly budget should be less than or equal to $1,000. You can spend less than that, and then you have money to save. And so that's why constraints are inequalities. You know, if you're maybe you want to budget is always a constraint. You might have some constraints in materials that you're using to make. Maybe you want to fence in a yard for your dog, but you only have 50 feet of fencing. So your perimeter of your yard would be less than or equal to 50 feet because that's all the fencing you have. Okay, so it's a very common thing. It's a very common sense thing, etc. The solution set of the system of inequalities made up of the constraints contains all feasible solutions of a linear programming problem. And that's just that shaded area that's common to all, that the solutions are in there. Those are possible solutions. The function that we want to maximize or minimize is called the objective function, which makes sense, right? What is our objective? My objective in building the yard for my dog is to create the largest area possible so he has more area to play. The objective for my business is to maximize my profits, you know, as any business wants to do. All right. So to find the maximum or minimum value of a linear objective function subject to a set of constraints, you graph the region of feasible solutions. That's just looking for that intersection area from a system of equations, inequalities. Determine the coordinates of the vertices of the region, and it's just very important that you find the vertices, the corner points, where are the intersections between those lines, and then evaluate the objective function at each vertex. The largest and smallest of those values are the maximum and minimum values. Now that's probably not really clear yet, but you're going to have a objective function, right? What is the objective that you're doing? The maximum area of my yard. Well, when I look at those vertices, I'm going to have a formula for that objective function, area equals width times length. When I look at the feasible area, the corners of that feasible area of that intersecting, I'll use those x and y values, or width and length, in that example problem. Okay, it's easier or more clear once you look at a problem. All right, let's look at an example. A tray of corn muffins requires 4 cups of milk and 3 cups of wheat flour. A tray of pumpkin muffins requires 2 cups of milk and 3 cups of wheat flour. There are 16 cups of milk and 15 cups of wheat flour available. Now I put this in red because I wanted you to see these are the constraints, right? I only have 16 cups of milk and I only have 15 cups of flour. So I cannot make more, I can't make these muffins if I need more flour or milk. The baker makes $3 per tray profit on corn muffins and $2 per tray profit on pumpkin muffins. How many trays of each should the baker make in order to maximize profits? Okay, so the first thing we want to do is identify some of these equations. And in order to do that, we need variables. Remember, the variables are what the question. How many trays of each? Now, when we're talking about each, we're talking about corn muffins and pumpkin muffins. So we need C will be the number of trays of corn muffins. Notice I didn't use X. And P is the number of pumpkin muffins. If we do that, we know that we make $3 per tray on corn muffins. So a profit equals 3 times the number of trays of corn muffins, plus $2 per tray. So 2 times the number of trays of pumpkin muffins. So here is my objective function, which is what I'm trying to optimize. So P equals 3C plus 2 lowercase p. Okay, lowercase p is the number of pumpkin muffins. Big P is the profit, which we're trying to maximize, as is any business. We know that muffins require, these should be C and P here too, sorry. We know that corn muffins require 4 cups of milk and pumpkin muffins require 2 cups of milk, and that there are no more than 16 cups of milk, so we have our first constraint. 4 times corn muffins plus 2 times P is less than or equal to 16. We can do the same thing with flour. Corn muffins take 3 cups of flour, 3C. Pumpkin muffins take 3 cups of flour, 3P, and we have 15 cups of flour total. So 3C plus 3P is less than or equal to 15. There's a kind of a hidden constraint in almost all of these problems, and it's just a logical constraint. And that is that C and P have to be greater than or equal to 0. Now, why is that? Because I cannot have a negative number of trays of muffins. I can't have negative muffins. It just doesn't make any sense. And so that's one of the things that does. It really helps us because that will keep us in the upper right quadrant number 1 of the graph. So what we're trying to do is to maximize the profit function, which is called the objective function in these problems, subject to the constraints of milk and flour, and of course the fact that you cannot make negative muffins. I don't know if you ate a muffin if that would make it negative. I think that's just subtracting. Anyway, we graph the systems of inequalities and determine the vertices. Okay, so we're going to graph. Notice again that the x and y axis are part of this because it has to be greater than or equal to x, or C and P have to be positive, so they have to be in this top right quadrant. Okay, so this x and y axis in the first quadrant are part of our graph. Then we have our 2 lines here. in green and in looks like purple, and then this shaded area. So what we're going to do is we're going to find all of these vertices, what is the C and the P value, and plug them in. So we have one at the origin, 3, 0 plus 2 times 0 equals 0. We have one at 0, 5. I guess I'll go this way since they went counterclockwise. 4, 0. Let me see that when we plug that into our profit function, we get 12. We have 0, 5, which is here. We plug that in, we get 10 for profit. And then the last one is, looks like 3, 2. And when we plug that in, we get 13. We were trying to maximize this function. So what we want to do is look for the largest value here. And we can see that largest value occurs when we do 3 corn muffins and 2 pumpkin muffins. Okay, 3 corn muffins and 2 pumpkin muffins. If we were looking for the minimum profit would be we do nothing, which kind of makes some sense too as well. So the baker will make a maximum profit when 3 trays of corn muffins and 2 trays of pumpkin muffins are produced. Guys, that's it. You have covered all the material of college algebra. Reach out if you need any help, and the final exam is just around the corner.